Okay, so this is the first of the two NIRSpec notebooks. So this is illustrating how to run the pipeline, how to do the pipeline data reduction for extended sources observed by the NIRSpec IFU. In this case, we're looking at observations from the ERO program 2729 that are observations of the Tarantula Nebula. So again, with NIRSpec, it's the same overall scenario as for MRS. There are three stages. There's the detector 1 part of the pipeline, the spec 2, and the spec 3 part. The data naming, the file name convention of input and output products is the same, uncal and rate, and S3D, X1D, and underscore cal, and so forth. So again, do import statements at the very beginning. It shows you the pipeline version and the CRDS context being used. Convenience functions here just to be able to show images and to show the different types of data you can get from the cubes. So that one's a fairly long function. Here's a cell where, okay, so part of the cell is identifying paths for the data input and output directories, but also for the purpose of the JWebbinar, I've included this toggle switch where if I set JWebbinar equal to true, then it's only working on a single exposure for each of detector 1, spec 2, detector 1 and spec 2. I've already the data has already been pre-processed elsewhere, and so all of that data is used for spec 3. But this was just to save time. But yeah, if you were using the notebook to reduce data yourself, you could set it equal to false here, and then it would go through all of the data for each of the parts of the pipeline. Defining the CRDS path and context. Next. A bit on downloading the data. I'm skipping actually downloading the data because that would take a long time as well. But this is a table kind of summarizing the observations. So it's program 2729 of the Tarantula Nebula. This is using the three high-resolution gratings of NIRSpec. So getting a spectrum that's approximately 1 micron to 5.3 microns, roughly. There seems to be some sort of misprint. It's identified as G140H, but describes as medium. I have to go back and look at that. I think for this notebook, we're working on one of the G235H files. So products found in MAST, I think we kind of covered this information previously. It's the source type, it's the source tie APT keyword that preserves the knowledge from when you set your APT, when you define the source in the APT and you set it to either point source, extended source, or unknown. That's the keyword that's preserving that knowledge that gets propagated through the files as you run them through the pipeline. NIRSpec, the NIRSpec IFU will default to extended, and so here it's going to be processed as extended data. This is showing products that are found in MAST. So this is what a count rate image would look like from the NRS1 detector for one of the G235H exposures. So here, if you remember the slide from the introductory slides, you see the 30 slices arranged here. And so there are 15 up top and 15 on the bottom. And then in the middle, you see the dispersal of the light that went through the fixed slits. So but here the observation was intended for the IFU. So you see the IFU, the signal that went through the IFU and then into the 30 different slices arranged on the top and bottom with the wavelength roughly going horizontally. That's the direction of wavelength dispersion. Here, this is an inset of one of the next to bottom of the top half of the slices, a little square on that. And so you can see, like in this case, the signal, and then outside of the slice is both above and below at the top and bottom of the inset. So that's the count rate image, and then this is from the data quality map for the same exposure. So this is from a different extension in the same file, corresponding to data quality. This is where each pixel is receives a bit value, and so if you decompose the value of the pixel, you can break it down into the various values that indicate different kinds of things that we could indicate were wrong with that pixel, like if it were affected by this or that. And so that's why the pixels here would have different values. Here is an example looking at NRS2 for G235H, where we're showing the effects of a snowball. So here we're zooming on a different slice, and you can see that in the inset, it kind of has a bullseye pattern. There's this core that's high valued, and then it sort of goes down outside the core, and then it kind of comes up again for an annulus outside of the core, and then sort of tapers off outside of that. So the cosmic ray strike would have happened like in the core, and so it would have raised the signal, but the signal, it's not a localized thing, so the effects go out over a large area. The pipeline is able to account for it up to a certain point, and I believe that's why you get the signal that goes down sort of in the intermediate distance from the center of the bullseye, but then not beyond a certain distance. Effectively, what it's done to the signal up the ramp is it's more of a minor jump when you get far enough away from the center of the bullseye, and so it doesn't really correct that as well. So this is kind of like what happens when you're not doing much of anything to do the reprocessing. And so this is the data quality map that goes along with the same data. And so you can see even in the data quality, the bit values correspond to saying that there's something that went wrong here with the same sort of bullseye pattern. And this is just noting that the values in the data quality map correspond to different things that went wrong. And let's see, and also pointing out about snowballs. And then, so this is looking at the stage 2 output from MAST. So you can look at how the image looks at different wavelengths. Here's the spectrum at different locations in the cube. And then you get a weight map, which I believe is how much information went into determining each different part of the cube. And then the same kind of a preview of Spec 3, again, how the image looks at different wavelengths in the cube, the spectrum, and then the weight map. And because this is Spec 3, this takes into account all of the exposures that went into the observation. So you'll notice that the weight map is heavily weighted towards the center of the cube, and then there are less weights toward the edge, so less information went into the cube further out in the final output cube. Also, another reminder about outlier detection. I think I can point that out when we get to it, when we define the how the data is reduced. So the extract 1D step, you can specify how to extract within the extract 1D step. And let's see. So if you combine the spectra that you get from MAST, this is what it looks like. And so yes, you can identify that the continuum is kind of slowly rising to longer wavelengths, and you can see emission lines. But there's also other things like the sort of rippling that happens on the continuum that you can especially see at these longer wavelengths. So there's room for improvement over the mass data. So that's why we do this data reprocessing. Let's see. So stage 1. So this is like with the MRS notebook, we define how we want to do the processing for each of the stages. So here's stage 1. Again, JWebbinar equals true. We're only reducing the information for, reducing the data for one of the exposures. And so here we're specifying keywords for the jump step. Again, this is important. That and the ramp fits that are important for how to deal with the correcting for the snowballs. Also, the ref pick step is important to worry about as well. I believe later in the notebook it notes that this rippling that you see at longer wavelengths has to do with the pixel masks. So how we deal with the pixels is important. So anyway, this is where you set the keywords for individual steps if you, when you want to go back and do the reprocessing. And then run the stage 1 part of the pipeline. So there was, you get all the feedback and it processed successfully. And here we take a look. So this is an inset on one of the, I guess, the better behaved parts of the image. And you can see the signal from that slice and the inset. And then the same inset, but in the data quality plane, and you can see how the bit values are for different pixels. This is looking at the same images before that we got from MAST, from the archive. The same inset region looking at the snowball. And here we're looking at the count rate image, and while you can still see the effects of the snowball, you're mostly seeing it in the core. So the reprocessing that was done seemed to do a good job of correcting for the effects of the snowball further out in the bullseye pattern. And so that's also reflected here in the data quality map for the same data. Okay, that was detector 1, and then stage 2, the spec 2 part of the pipeline, and again specifying things for different steps in spec 2. So like here, we're saying skip equals true for the imprint subtract step, so it's going to skip that step. That pertains to leak cal observations, which we're not worrying about here. And so there are the other steps, skipping the background subtract step. And this is where, if you're doing the pairwise background subtraction, I think that's this step, and so we're skipping that here. Okay, and then it runs, and there weren't any problems. And then looking at the output. So again, this is where you get calibrated data, but only for individual exposures. So here is just looking at images at different wavelengths, 2.3, 2.5 microns, the spectrum that you get, and then the weight map. Okay, so that's stage 2. Stage 3, remember that stage 3 requires an association file. That's where you specify all of the different exposures that stage 3 will combine. And so here's where we define the association file in this step. and use it. And so here we're showing the association file. It has the structures that it has sort of some preliminary information at the top, and then at the bottom, you're specifying the individual exposures that will be, or the individual files that will be combined as part of the stage 3 part of the pipeline. So you'll notice that all of these file names under exp name have the same middle set of digits. In this case, 0, 2, 1, 0, 3. I believe that that's how this all would correspond to a single grading setting. I think that's how it works here. But these other numbers, so like this one is different. So those are different exposures for that grading setting. And then you specify NRS2 or NRS1. And notice these are the _cal.fits files. Those are one of the types of output from spec 2. And so those are the input here for spec 3. Okay, so that's the association file. And then run spec 3. And so here, remember again, it can be important to experiment with the outlier detection step. So if you want to try, if they've made changes and you want to try different parameters, you can specify that here. And then the cube build step and extract 1D step. There's a waiting keyword for cube build that defines how the cube is, that's the algorithm implemented to create the cube from the raw cloud, three-dimensional cloud of data. And here the MSM is short for modified Shepherd method. That's one of the methods. Another one is drizzle that are used. This is the output type keyword. The value is set to multi, which I think, yeah, it describes it over here, that it combines into a single Uber IFU cube that combines everything. But here that's commented out, so it wouldn't see that. And then so stage 3 runs, and here there were no problems. So that was a successful run. And then showing the results. In this case, we're combining the data for different grading settings. So you get the different you get images from the cube, different spectra, and then the weight map. And a reminder that if the source type is extended, then the extraction aperture is the whole cube for extract 1D. And then finally, comparing both the masked spectrum and the reprocessed spectrum. The masked one here is grayed out, and you can see that the ripples that especially show up at the longer wavelengths. And then the one that we reprocessed here is from the 3 different grading settings, or the 3 different colors, the red, teal, and darker blue. And so here in the darker blue, for instance, you no longer see these ripples, which I think have to do with issues with the pixel mask. Okay, so that's it for that notebook.